Good morning, friends. We meet again for the next session of our stresses in the beam. The stresses in the beam have been divided into two parts, that is bending stresses in the beam and shearing stress in the beam. And in the last two lectures we had completed our bending stresses in the beam. Today we start with the shear stresses in the beam. So my today's session will have shear stresses, that is shear in straight members, then shear formula, that is we are going to derive the formula for shear stress in the beams, and then we'll derive the formula for a rectangular section, the stress distribution along the rectangular section. So to start with, first of all, shear stresses in the beams of a rectangular cross section. So in the previous chapter we examined the case of a beam that is subjected to pure bending, that is a constant movement along axis. When a beam is in pure bending, the only stress resultants are the bending moments, and the only stresses are the normal stresses acting on the cross section. So we all know that whenever a beam is subjected to transverse load, then there are development of shear force as well as bending moments. The bending moments are responsible for the bending stresses, whereas the shear forces are responsible for the shear stresses. So when the bending moments are responsible, they try to produce, either we call it as normal stresses or we call it as the bending stresses. Most beams are subjected to load that produce both bending moments and shear forces. So we know that the algebraic sum of the moment of forces acting either to right or to the left of the section is called as bending moment, and the unbalanced vertical force which is acting either to right or to the left of the section is called as shear force. So these two produces either normal stresses or bending stresses and shear stresses. Now you can see in this particular diagram the longitudinal stresses as well as the transverse stresses. V is basically nothing but the unbalanced vertical force. You can see it is acting in the vertical downward direction, right? So V is the vertical unbalanced force, and that vertical unbalanced force is trying to produce the transverse shear stresses, which is represented by the symbol tau. Okay. Internal shear force creates shear deformation, strain and shear stress. Due to nature of shear stress, get transverse and longitudinal strain. Now you can see this is a beam. If you can see, we have drawn a figure showing the layers of the beam, right? We can see over here 3 wooden planks which are not bonded together in the first diagram, and it is subjected to a vertical force, or we call it as a transverse force. The second diagram shows that all these 3 planks or boards are now bonded together and they are supported at both the ends, so we can call it as a simply supported beam, right? Now if you will, physical example which I am showing in this particular diagram is when boards are glued together, the shear stress is developed at surfaces which prevents slippage, right? So in the first diagram, when we are not bonding it together with the help of a glue, there are chances of slipping, but to prevent the slipping we are trying to glue it or bond it together. Key point is deformation. Deformation is not uniform, right? You can see in the first diagram we have a horizontal structure, okay, but due to the unbalanced vertical force there is some deformation taking place, but the important point is that the deformation is not uniform throughout. At the edge it is less, and then it is keeping on increasing as we move towards the fixed end. So in these cases both normal and shear forces are developed in the beam. You can see the symbol of moment, that is bending moment, which is denoted by M, and a vertical force which is denoted by V. So we can say that if we are taking a simply supported beam and we are taking a section X from the left support, then the section X at section X we have got vertical unbalanced force V, which is equal to a reaction at support A, that is RA, and a sagging moment, that is RA into X, or we also call it as V into X. So normal stresses are calculated with the flexure formula. Now if you remember what is a flexure formula, in the last lecture we had derived the flexure formula, that is bending stress theory my phi, that is M upon I is equal to FB upon Y is equal to E upon R. So using this particular formula we are going to derive the normal stresses. Vertical and horizontal shear stresses. Consider a beam of rectangular cross section which is subjected to a positive shear force. So we are considering a rectangular section. You can see that we have taken a three-dimensional, that is X, Y and Z axis. So along X axis we are showing the stress or the bending stress along X direction multiplied by dA, and along Y direction tau xy, that is if the bending stress is along X direction, then there will be transverse stress in the vertical direction, that is tau xy, and in the Z direction. So this diagram shows the development of transverse shear stresses as well as normal shear stresses. You can see the second diagram, it is showing the flexural rigidity, or we can say flexural stresses, that is stresses developed due to bending moment, right? So M, that is bending moment, and due to this bending moment we have developed the bending stresses. Now to derive the shear stress formula we have to make certain assumptions. So shear stresses are parallel to the shear forces. Shear stresses are uniformly distributed across the width of the beam. Using these assumptions we can determine the intensity of the shear stress at any point on a cross section. You can see that the initial state is exactly horizontal. After loading we can see that is slip at the interfaces, and the shear stresses is developed when the slip is restrained. If the planks are bonded together to form a single beam, longitudinal shear stresses must develop to prevent the relative sliding between the layers. There is a maximum shear distortion at the middle plank, while distortion is zero at top and bottom of the beam. And now basically to explain this, I'll have a very simple theory that we have already studied, that is what we had studied is the basic theory that when we are having a relationship between shear force and bending moment, so we know that when shear force value is 0, or shear force is changing its sign from positive to negative, at that particular point the bending moment value is maximum, right? Now if we use this particular concept for our bending stress, what we know that if I am taking a rectangular cross section, right? So if we are taking a rectangular cross section, if I want to find out the CG of this particular section, so the intersection of the diagonals will give you the position of CG, right? Now the point at which the CG is obtained, the line passes, is called as centroidal axis, or we call it as a neutral axis, right? Now if we have got a sagging bending moment, then we know that the top layers above the neutral axis is subjected to compression, and the layers below the neutral axis is subjected to tension, right? Now if I want to draw a bending stress diagram, so we know that the bending stress is maximum at the center, bending stress is maximum at the top and at the bottom, and is 0 at the neutral axis. This all we have studied in our previous lectures. So at the top we have got bending stress and compression. At the bottom we have got bending stress and tension. Right? If we have got a second bending moment. Now if I want to draw the shear stress distribution, then where the value of shear force is 0, right, the bending moment is maximum. So vice versa, if I say that if the value of bending moment is 0, at that particular point the shear stress value will be what? Maximum, right? Similarly, where the bending moment value is maximum, shear stress value will be what? 0. So at top and bottom the shear force or the shear stress value is 0, and where at the center the bending stress is 0, there the shear stress value will be maximum, right? So this is what I have shown in my, these lines basically show that there is a maximum shear distortion at the middle plank. So this is the middle plank where you can see the maximum distortion, and it is 0 at top and bottom of the beam. So 0 at top and bottom of the beam. Because of shear deformation, plane sections do not remain plane. That means the sections which were exactly horizontal will not remain horizontal, but there will be some deformation taking place due to the shear development. This is in contradiction with the theory of pure bending, in which plane sections were assumed to remain plane after deformations. If you recall, when we had derived our bending stress theory, we had assumed that the sections will remain plane even after the deformations. So in this particular case it is not same. In this particular case we are assuming the sections will deform after the loading. Okay, so that is a contradiction. So we will assume that the shear deformations have little effect on the distribution of the flexural stresses as long as the beam is slender. So the length is at least 10 times the depth. So now we will derive a formula for the shear stresses in a beam. So we will consider a beam having a length L, right? So this is our derivation. Consider a uniformly distributed load acting on a beam of length delta x. So you can see this particular diagram. In this particular diagram we have taken a beam of length L. We have taken a beam of length L and it is subjected to uniformly distributed load W kilonewtons per meter. We are taking a small length delta x and we are taking two faces, face AB and face CD, right? At face AB, let the bending moment be M, and at CD the bending moment be M plus delta M. Similarly, at face AB, let the shear force be F, and at face CD the shear force be F plus delta F. We know that as we move from AB towards CD, there is increase in bending moment as well as shear force. Now the bending moment and the shear force will keep on increasing as we move towards left to the right. We are taking a small layer EF which is lying at a distance of y with respect to neutral axis. We all know how to locate neutral axis. The neutral axis is located by finding out the CG of the section. The point where the centroid is obtained, the axis is called as centroidal axis as well as neutral axis. So you can see over here we have found out the neutral axis. Now we want to find out what is the unbalanced vertical force acting. So before finding out the unbalanced vertical force, we are going to take the elementary strip which I have shown, that is EF. Now the bending stress will be developed due to the bending moment. So the bending stress is denoted by F. In certain books it is denoted by sigma. So F or sigma both represents the bending stress. So if I take my face AB of the rectangular section, so at face AB the bending stress produced due to bending moment M will be F. Similarly, at section CD the bending stress developed due to bending moment M plus delta M will be F plus delta F. So this is the bending stress theory which I have written, that is M upon I is equal to F upon Y is equal to E upon R. So our formula will be F, that is equal to My upon I. So F plus del F, that will be equal to M plus del M upon I into Y. So force acting across the section AB. Now we know that what is stress? Stress is nothing but force per unit cross-sectional area. So if I want to find out the value of force, so what will be force equal to? Force will be equal to stress multiplied by area, right? So now force acting along or across AB, that is nothing but stress into area. And what is stress? F into A. So F into A, but stress F, that is nothing but force upon area. So we are substituting over here force, that is equal to My upon I into area, that is A. Similarly, if I talk about the force acting across the section CD, then it will be F plus del F into area A, and the bending stress can be replaced by our equation M plus del M into Y upon I. So we are getting two equations for forces across section AB as well as across section CD. Therefore, the net unbalanced force which will be acting on the strip EF, right? So net unbalanced force which will be acting along the strip EF will be M plus del M I into Y into A minus M upon I into Y into A. So the unbalanced force that we are going to get, that will be delta M upon I into Y into A. Now this total unbalanced force above the neutral axis can be obtained by